Right. Welcome to the sixth session of the /SIGME training. I'm Stella Kim, and I'm an assistant professor at the University of North Carolina in Charlotte. I currently serve as a co-chair of the Scaling, Linking, and Equating SIGME with the other co-chair, Jamie Malatesta. So today I'm going to be the presenter of this session. So there will be no moderator. I will be serving both as a moderator and a speaker. So I will need your help to see if you can view my screen. If there is any issue with viewing my screen, please let me know because there will be no moderator. Right. I will just give you a short introduction to myself. I am a University of Iowa graduate. I graduated from the university in 2018. And as you may guess, my dissertation was to develop a multidimensional IRT true score equating method. So that's how I ended up having this session for you today. So I guess there are some specific needs for those of you who attend this session. First of all, I'd like to thank all of you for joining today with this session. So this session is going to be a bit distinct from the previous sessions in that the topics that are discussed during the session are still evolving, and the contents are recently developed. So the research area is still its infancy. So that's going to be some distinctions from the previous sessions. And I also assume that you also have some knowledge in equating and IRT, such as equating designs and IRT equating procedures and so forth. So I assume that here I have a special group of researchers and psychometricians who are interested in advanced topics in equating. So the intention of this session is to provide kind of the review of the current literature and to suggest future research areas. Okay. Feel free to type in any questions during the session into the chat box if you have any. And I'd like to address these top questions during the session if you have any question. And feel free to unmute yourself and ask a question if you have any during the session. Okay, and then the slides will be made available after the session from the shared Google Drive. So I'm sure you received my email, which was sent yesterday with the link. So there is a Google, the link for the Google shared drive where you can find all the materials for the session activities. So I'm gonna put the slides onto that Google share folder. Okay. Any questions or any questions? I think I'm gonna just start the session. Right. Let me share my screen. Can you see my screen?
Yes.
Thank you. Right. So today I'm going to talk about the multidimensional IRT response theory equating, which I often call it as multi-equating. As I already introduced, I'm Stella Kim, and these are the topics that the contents that I'm gonna discuss today. So first, I'd like to talk why we want to do multidimensional IRT equating, like why we want to consider this, advanced or more complex equating method. And then I'd like to give you a short introduction to the multidimensional IRT models that are that have appeared in the equating literature. And then I'm going to do some review of the current literature on multidimensional IRT equating. And then I will walk through with you on the process of the simple structure, multidimensional observed score equating. And then I'm going to do a simple activity using the programs that I shared. And then finally, I will wrap up this session by providing some potential research areas that I think I think it's important. So that's the content, right? Let's get started. Let me first discuss why we may want to consider using multidimensional IRT equating. So as you may know, there is a strong assumption required by IRT, right? Which is the unidimensionality assumption. So that assumption dictates that only a single ability is measured by items in a test. We know that this is quite a strong assumption, right? So, previous research, fortunately, has demonstrated that the results from IRT application are quite robust to the violation of the unidimensionality assumption, which is quite fortunate, right? But this assumption has been challenged in the literature that educational processes are very complex and constructs to be measured cannot be fully captured or represented by a single latent trait. So I think that's the origin of the concept of multidimensional IRT. Basically, no single test is unidimensional, and all tests are inherently multidimensional. So we may expect that the responses to an item are not solely dependent on on a single trait or a single ability, right? So now the issue becomes it's not a matter of whether a test is unidimensional or multidimensional. Rather, the central question here becomes to what extent the test is multidimensional, and what are the consequences of violating the assumption of the unidimensionality. Okay, so it's not a matter of whether the test is unidimensional or multidimensional. Essentially, all tests are multidimensional. And we'd like to know what are the consequences of violating that assumption and to what extent the test is multidimensional. So possibly there are, I guess, tons of sources of multidimensionality, right? But the literature provided some major causes of multidimensionalities, and I listed those major causes of multidimensionality in this slide. So the first thing is the content domains. So if a test consists of a distinct set of content areas, then we may, imagine that the content difference measured by a set of different items can cause some multidimensionality in the test, right? The second one is the using a multiple item formats. For instance, a test might involve both multiple choice items and constructed response items. In previous studies kind of demonstrate that responding to constructed response items may differ from responding to, or may require different set of skills than to responding to a multiple choice items. So if a test involves involves different types of item formats, then they may cause, it's not necessarily, but it may cause some multidimensionality in a test. The last kind of source of the multidimensionality that I found from the literature is to use a common stimuli that a subset of items share. for instance, we call it as test lead, right? So if there is a common stimuli that a certain, a subset of items share, then that kind of dependency, item dependency among those set of items may cause some multidimensionality. So this is not the complete list of the causes of multidimensionality, but this is kind of like a major causes of multidimensionality. Right. So researchers in the measurement field started recognizing the benefits of using multidimensional IRT models, which led to numerous applications in psychometrics. So I guess the first models were developed or appeared in the literature in 1960s by Lord and Lubick and McDonald. So they developed the compensatory multidimensional IRT models, and I guess that's the very first models that appeared in the literature. So since its inception, the multidimensional IRT has been applied in many psychometric procedures, including differential item functioning, test construction, scale linking, test equating, and possibly, I think it's computer adaptive testing as well. So in terms of the, so what are the impacts of violating that assumption on equating? So in terms of that impacts, previous research indicated that if there is a kind of like a moderate or strong, high level of multidimensionality in a test, that may lead to poorly estimated item and person parameters, which necessarily leads to inaccurate equating results because we use these parameters to do IRT equating, right? So again, the focus here is not to evaluate whether a test is unidimensional or not, but how much we can tolerate with the central question is how much we can tolerate with the violation of that assumption, and to evaluate the impacts of that violation on equating results. So to me, if data clearly suggests multidimensionality, and the presence of multidimensionality is evidenced or supported by the theory or the test specifications, we may consider to use multidimensionality, multidimensional IRT equating. All right, so next, I'm going to explain a few multidimensional IRT models that are introduced in the equating literature using this visual representation. So here you see there are 4 different models at the top: unidimensional IRT, simple structure, multidimensional IRT, bifactor multidimensional IRT, and full multidimensional IRT. So as you may guess, there are more models exist. So this is not the complete list of models we can think of to do multidimensional IRT equating, but these are the kind of models that are presented in the literature, the equating literature. So that's why I wanted to focus on those 4 models during this session. So I'm going to present a set of visual representation of the model, and you will need to give me the answer which model will fall into which model. Okay. So here first, I'm going to start with this model. You see there are 6 items in the test, and there is one latent trait, which is denoted as theta G. Okay. Seems like there is only single theta, which is intended to be measured by a whole test, and responses to these 6 items are affected only by this single latent trait. And here you see there is a theta G. The G indicates that it's a general ability. So the central or the primary ability that is intended to be measured by this set of items. Okay, so which model this one will be? Can you guess? If you have any answer, please type in your answer to the chat box. Is it unidimensional? Yes, it's a unidimensional. Thank you. So it's going to be under unidimensional IRT. There is a single ability, and then all the items in the test will be affected only by this single latent trait. Okay, next one. So I have this different model. You see there are two different latent traits. So previously we only had one theta G, but here we have two major thetas, right? So there's a theta G1, and then there is another theta G2, okay? And same here, we have 6 items, and each item is impacted by both theta G1 and theta G2, right? So each item is explained by both abilities. So do you think which model this is going to be? Any answer? Bifactor, possibly. Bifactor, full mode. Okay, so the answer is, this is full mode. Okay, because each item is affected by all the latent traits in the model, specified model. So this is called a full multidimensional IRT model. Okay, let me give you another model here. So we still have 6 items, but you will see that there is a cluster of items. So here's one cluster that involves item 1 to item 3, right? And then another cluster that includes item 4 to item 6, right? And each item loads only a single factor. So compared to this one, you will see each item is going to be affected by both theta G1 and theta G2, right? But in this case, you will see each item loads on a single item. No, single factor, sorry. And then there is a correlation between those two thetas. Yes, the answer is, it's a simple structure. So the main difference between these two models, or probably these two models. So this one is a unidimensional IRT model, and these two are multidimensional. You can say these are the multidimensional models. The difference, I think the main difference is that for the simple structure model, you have to have a priority data structure in mind, right? Like if you want to analyze data, you know which item is going to be loaded, on a certain factor. Whereas here under the full multi model, you don't have to have it because all items will load every single factor that is specified by by researcher. So for this case, it's more like exploratory, whereas this one is more confirmatory, right? And in the literature, some researchers called or are referred this to as within item multidimensionality. So it occurs, the within item multidimensionality will occur when each item in a test measures more than one latent trait, more than one latent ability. Okay, but in this case, in the literature, in case of the simple structure model, people call it as between item multidimensionality. So in this case, a test consists of multiple unidimensional parts. So let's look at let's just focus on those 3 items, right? If you just disregard the rest of these items, it's just a unidimensional IRT model, right? And here's another unidimensional part, right? So for this case, we call it as between item multidimensionality. Okay, again, the difference between these two models are this is more exploratory. So meaning that you don't have to have a priority data structure design for analyzing the data. But for this case, you have to have that design in mind to analyze data. So, for item 1 to 3 will load on the first factor. Item 4 to item 6 will be load on the second factor and so forth. Okay, right. The very last model is going to be the bifactor model. So as you can see, there are some variations in the model, but the distinction from the unidimensional IRT model is that, for all these multidimensional models, we have multiple latent traits involved in the model, right? Whereas here we only have a single latent trait. Okay, let's look at the bifactor model. So there is one general factor, which is denoted here as theta G. Okay, and then there are 2 more specific thetas. So I used S to indicate that it's a specific theta. So very similar to this one, right? So there is like a cluster of item here, another cluster of item here. So we can use these models if there is a testlet in a test form. So say there is a single passage, there's a passage associated with these 3 items, and then another passage associated with these 3 items. For that case, because that item dependency within the passage may cause the multidimensionality, we can use the bifactor model to capture that dependency. So if you use the if you use the traditional IRT model for multidimensional data, you often have higher reliability. So meaning that you overestimate reliability and underestimate measurement errors, because you ignore that extra dependency among items. So because we want to capture that dependency among items, but that dependency is not solely due to the major or the primary latent trait that we intend to measure. We want to capture or kind of like disentangle that factor and have it in the model to capture it. Okay, so for this case, we have a specific 2 specific thetas, and there is a single general factor. And if you look at the item level, there is an item with each item loads on both specific factor and then the general factor, right? So if you look at each item will load on a single specific factor and a general factor. So it doesn't matter how many clusters of item exist in the model. If you have like a third cluster of item, that cluster of items will still have a general factor and a specific factor. So if you increase the number of dimensions, it doesn't increase the number of factors that are affecting each item. Still, each item will be represented by a single specific factor and a single general factor. Okay, right. And then often these thetas are assumed to be mutually orthogonal, meaning that their correlation are specified to be 0. Okay, so I got a one question from an attendee. What's the difference between the bifactor model and testlet model? So in this model, in this bifactor model, we have the latent trait to indicate the specific theta. As far as I know about the testlet model, there is no theta, like the Pearson parameter, to indicate the testlet effect. So there is a testlet effect parameter, but it's not, that parameter is not associated with the Pearson parameter. So there is still a single Pearson parameter, but there is a parameter to capture kind of like a testlet level parameter to capture the level of dependency among those items. Did I answer your question? Yes, yes. But still, you can capture that that kind of level of item dependency using that parameter. Right. Great. So, right. So now, as I kind of review the models that appeared in the multidimensional IRT equating literature, I'm gonna give you a simple or brief review of the current literature. I hope that this kind of gives you an idea where we can go and where we are. So this is where we are, and as you may see, there are not much research that has been done in the field. So, as you can see here, the very first work was done by Lee and Brossman in 2012, which is about like within a decade. And then these are, I guess, 7 research papers that are presented in the literature over those 9 years. And these 9 pieces of research was to develop multidimensional equating methods. Okay, let's look at some details about each of these methods. So you see there is a simple structure multidimensional observed equating proposed by Lee and Brossman, and they use the real data. And then following year, they also developed a full MIRT observed score equating. So you may know that in IRT equating, there are 2 types of equating procedures, right? Which are the true score equating, where we use true scores, the relationship between true scores to find the old and new form relationship, right? And there is another equating procedure called observed score equating. So under the observed score equating, we use the marginal distribution or model fitted distribution, and we do equal percentile equating to find the relationship between old and new forms. Right. So as you can see, some people developed observed score multidimensional IRT observed score equating method, and some did for the true score equating, and some did both. As you can see here, most of the research was conducted under the random groups design. I'm gonna tell you. I'm gonna discuss why this was the case by pointing out some challenges associated with the true score equating. Another thing that we can look at is, actually, this is my research. This is out of my dissertation, and I use both random groups and common item non-equivalent groups design. Sorry, this stands for common item non-equivalent groups design, or some people call it as NEAT, the non-equivalent groups design with anchor test. So I conducted the I conducted that research under both random groups design and common item non-equivalent groups design. But prior to my research, all these works were under the random groups design. Most of studies have used the simulated simulation, technique, have used the simulation technique to evaluate whether that proposed model worked better than the unidimensional IRT equating method. Okay, so as you can see, there are not many papers yet in this field. Right. And then the next table shows the study that compare different equating methods. So initially, this table shows the summary of research that proposed a new method using one of these multidimensional IRT models. And then this table shows the studies that compare multidimensional IRT equating methods in a certain context or using a specific simulation factors and so forth. Again, there are not many still, right? Only 5 studies, comparison studies in the field. And as you can see, some of them used the random groups design. And then more recently, people kind of started paying attention to the common item design as well. So the more recent work was conducted under the common item design. Okay, so I didn't include the unidimensional IRT model here, but in most cases, almost every study included the unidimensional IRT equating method as a kind of like a baseline equating method to compare these methods with that existing model, existing IRT, unidimensional IRT equating method. So most of them used simulated data. And then, yeah, that's it, right? So here is the review, kind of like summary of the review of the literature. So multidimensional approaches provided more accurate equating results for multidimensional data. That's the kind of key implication or message that these previous research kind of collectively tells us, right? So I have the R here, right? So the R in this slide indicates the correlation between dimensions. Okay, so for instance, here under the simple structure model, we can estimate the correlation between these factors, right? So if this correlation is high, like 0.95, what would that indicate? So say like the correlation between 2 factors was like 0.95, okay? It kind of indicates that the test is almost unidimensional, right? Because 2 factors are not distinct from each other, right? They are almost the same or similar construct. So they share some, high level of similarities or share some, like share lots of like variance, covariance between these 2 factors. Then essentially it means that the test was not very multidimensional, right? But if this correlation gets, lower, like 0.6, 0.7, that means each item, each factor is going to be measuring somehow distinct, ability, right, from each other. So I often look at the correlation between factors or true scores. If you're going to use the discontinuous correlation, and also you can also kind of compute the discontinuous correlation among, among those dimensions, right? If that correlation is lower than 0.8, I guess that's kind of like a benchmark where we can kind of start thinking about using a multidimensional approach over the unidimensional approach. But anyway, my point here is that if that correlation is lower than 0.8, meaning that the tests are, substantially multidimensional, then the multidimensional IRT models tended to provide more accurate results compared to the unidimensional IRT equating method. There are several study factors that were examined in the literature. These included a degree of multidimensionality, of course, test length, sample size, form difference, if there, and then sources of multidimensionality, and the number of dimensions. So these are kind of like factors that often appear in the literature, in the multi-equating literature. And as I kind of pointed out already, most research was conducted under the random groups design, except for only a few recent works. And as I already discussed, more attention has been paid to observed score equating than to true score equating. So let me give you the idea, like why that was the case. Right, so just a brief review of the true score unidimensional IRT true score equating. Okay, so now we have, in this slide, we have the TCC, right? Test characteristic curve. So we have a new form with indicated by the dashed line, and then the old form indicated by this orange solid line. Okay, and this is the test characteristic curve. So in this scenario, I had 10 items. So the sum score goes from 0 to 10. And then the x-axis indicates the theta value, right? So my goal here under the unidimensional true score equating, my goal is to find the scores that are corresponding to the same theta score. Okay, so let me first let me go ahead and explain what I'm gonna do. So, okay, I'd like to find the equivalent equated score for a new form score of 4. Okay, what we do to do that is to find its corresponding theta score. So we start from this, score on new form, and we find the corresponding theta score, which was -2. Okay, and then we find that corresponding true score on the old form, because they share the same theta score, right? We can kind of consider that this new form, the score of 4 on the new form is equivalent to a score of 2.8 in the old form. That's how we find the relationship between new form and old form under using the unidimensional true score IRT equating, right? So that's the review of this true score equating procedure. I'm sure Jamie last week discussed, she provided more detailed description of this procedure. Okay, right. Now, the challenge associated with this multidimensional space is that, as you can see here, like for instance, this scenario has 2 dimensions. Say there are 2 thetas for every examinee. Okay. Although I here I only had like item characteristic surface, you can kind of extend that now, to the test characteristic surface. So now, compared to this case, we have the test characteristic curve, right? Now we have the test characteristic surface. It's not a single curve. It's a surface, right? So my goal is to find the theta score that corresponds to a certain true score or probability if it's at the item level. Okay, so say I'd like to find the theta values that correspond to a probability of correct response on a particular item of 0.04, sorry, 0.04. There is a line, right? Because it's a surface, if you cut it this way, there is a line that gives you the answer for that question, right? So then my question becomes, which pair of theta 1 and theta 2 should be used to find that relationship? So it's easy here, right? Because there is a single theta value. So if there is, if you'd like to find the theta value, I mean the true score value that corresponds to the specific theta, you can identify that, right? But here, that becomes more complex because there is a pair of thetas, and virtually there are tons of theta combinations that you can come up with that may lead to the same true scores, right? That's the challenge with the multidimensional true score equating, right? So in the literature, I think still nobody has kind of reserved this issue in terms of true score equating. So people use kind of like projection method or like integration method to kind of integrate out, you know, sub-dimensions or specific dimensions or so forth. But because of this issue, true score equating under the multidimensional approach has not been really elaborated or sophisticated yet. So, but I develop a specific procedure to kind of bypass this, you know, this complexity. So if you'd like to know more about this, you know, procedure, you know, the procedure that I developed, you may refer, you may see this article. I also provide a list of references that I had in these slides at the end of this slide, so you can, you know, check it out. Right. So today I'm going to talk about, so that's because of the complexity associated with the true score equating, multidimensional true score equating, I'm going to focus on a multidimensional observed score equating today, right? So if you attended the session led by Jamie last week, you may have a chance to learn how to do the observed score equating, IRT observed score equating using a traditional unidimensional IRT models. Okay, so basically, first, what we do is to calibrate items. The first one is we need to get the, you know, item parameter estimates, right? And then using the Luhr-Wingerski formula, we construct the conditional distribution given theta, right? And then we find the marginal distribution over those entire ability distribution by integrating, you know, conditional distributions. Okay, and then after you find you define the marginal distributions or model fitted distributions for old form and then the new form, we conduct the you know, equal percentile equating to find the relationship between those two forms. Okay, and get the result. Okay, right. So same here. It's not really different from the traditional unidimensional IRT equating method. So the same procedure will apply to every observed score multidimensional equating methods. Right, so I'm gonna go over this slide with an example of a simple structure models. So in this simple scenario, let's assume that there are 2 dimensions. So it's very similar to what I presented here. So basically, in terms of the observed score, IRT observed score equating, very similar procedure will be used regardless of the model that you choose. Okay, so if you go back to this slide, today I'm gonna focus on the simple structure model. But if you'd like to use a bifactor model or a full model, the very similar procedure can be used. But the only difference is how to construct the conditional distribution. Okay. So in this case, we have 2 different general factors, right? That's going to be the scenario that I will have for this. Oh, sorry, this. Yeah. For this scenario or for this case. Okay. So if you're going to use a simple structure model, basically you have multiple unidimensional parts. Right? And these unidimensional parts will be somehow associated through that correlation factor, right? But anyway, as I mentioned before, each item will load only on a single factor. So basically, it's very similar to the unidimensional IRT model, but the only difference is you have multiple theta values for every examinees. So if there is an item that is tapping on the first dimension, you're going to use this formula, right? In case of the 3PL model. So in this case, I'm going to use the 3-parameter logistic model, but of course, other models can be used, like graded response models or partial credit models, 2PL model, whatever model you'd like to specify. But in this particular example, I'm going to use the 3PL model just for demonstration purposes. So we have theta 1 and theta 2. And if that a certain item is tapping on the first dimension, we use this formula. And the other items, there should be some items that are going to be tapping on the second dimension. So you use this formula. So basically the difference is whether you use a theta 1 or theta 2, right? That's the only difference from the unidimensional IRT equating, right? And from the session last week, we know that the Lord-Wingersky formula is going to be used to construct the conditional distribution. The conditional distribution conditioning on a specific theta, right? But here, instead of a specific theta value, a single theta value, we have 2 theta values for each examinee, right? So it's going to be a vector of the theta. And we use that, the vector of theta vector to construct the conditional distribution using this Lord-Wingersky formula. I mean, the procedure is very similar to the unidimensional IRT model, but the difference is whether you use theta 1 or theta 2, depending on the data structure that you specify, right? Right. So the next step is going to form a marginal distribution, marginal observed score distribution, or some people call it as model fitted distributions, right? So here, because we kind of assume that there will be 2 dimensions in our model. We have theta 1 and theta 2. And this one is the conditional distribution that we developed from this slide, right? And then this is the the distribution of the latent trait, right? Often specified as a normal distribution under the unidimensional IRT procedure. And then we'll integrate, right, it over the entire latent trait distribution. So instead of having a single integration, we'll have double integration because there are 2 latent traits, right? But often that integration is approximated or replaced by the summation because to ease the computational complexity, right? So we often use this equation instead of this one, right? Here, the only difference, distinction from the unidimensional IRT equating method is that we use the bivariate. In case of 2 dimensions, but more generally speaking, it's going to be a multivariate normal distribution. So in the unidimensional IRT equating, we often use a standard normal distribution as a latent trait ability distribution, right? But here we're going to use a multivariate normal distribution to do this work, okay? Because there are 2 dimensions. I'm going to use a bivariate normal distribution, but if you have like 3 dimensions, you're going to use a trivariate normal distribution. The only difference, I guess, from that, a distinction from that unidimensional IRT approach is that there is a correlation factor, right? So it's going to be the matrix 0, 0, 0, 1, and then there is like a correlation factor between those 2 factors, right? So if you look at the quadrature weights and quadrature points and weights for this case, it will be looking like this. So, I assume that you know what the quadrature points and what the weights are, right? In case of the unidimensional IRT model, we have only a single theta and there is associated, corresponding quadrature weight, right? But here in this case, we have 2 thetas, and each pair will have their corresponding quadrature weight. Okay, so here, say we specify the quadrature points from -4 to +4, and then there can be all different kind of combinations between θ1 and θ2, and we can also identify the corresponding quadrature weights for each pair. So that's going to be the kind of like quadrature weights and quadrature points for this computation. Okay. Any question so far? It's like there is. Okay, let's move on. Yeah, that's a great question. So there is item parameter linking procedure. So today I'm going to just focus on the random groups design, but I will briefly talk about the separate calibration and the linking procedure for the multidimensional IRT equating. Yes, there is some noise from. Okay, so after you find, compute or construct the marginal distribution for both old form or new form. Old form is often denoted as form Y, and then the new form is often denoted as form X, right? So if you, once you find that marginal distribution for both forms, it's basically the same. Like you just do the equal percentile equating to find the relationship between form X and form Y. Right. And this one, the conditional distribution, is found from the previous slide that I just mentioned. So I guess it's time to take a break. So it's 1:55 here in Charlotte. So let's take a 10-minute break and come back by 2:05. Okay. Thank you. So now I'm gonna do some activities which may be interesting to you. I share some docs, some documents with you prior to this session. So if I'm sure you have that access to that data. I ask you to have FlexMert and RageRG equate during the session, but it's not required. I can simply demonstrate what what you can do using those data sets and then files, and then later on you can play with these files on your end. One thing that I like to highlight is that in order for us to do multidimensional IRT equating, we need to estimate item parameters using those models, right? Whatever model you're going to use, but we need that estimation part, right? As part of the equating procedure. But at this point, there are not many software programs that allow us to estimate parameters using a multidimensional IRT model. So I had a hard time to find the software for this session. Of course, FlexMert is not freely available. You need to pay to get a license. There is a R package called MERT, MIRT, and it allows for estimating, allows to estimate parameters using various types of models. But when I look at that function, there was no functionality that gives us the marginal distribution. That's what we need to do the observed score equating, as I explained. Like we need to get the marginal distribution, but there was no functionality in that package. So I had to determine to use a FlexMert, and I'm so sorry for those who have no access to FlexMert. But anyway, that's the main reason that I asked you to have the FlexMert. This activity, okay, I'm going to share my screen. In this activity, we're going to use the random groups design. So the equating procedure will be implemented under the random groups design. And then the equating methods we're going to use is the simple structure multidimensional IRT observed score equating, which I just provide you some details about, and then there are two data sets. So you will see that there are data.x, data-x.txt, that's the data for form X, the new form, and then data underline and y.txt, that's the data for form Y, the old form. And if you look at the data, you will notice that there are actually 43 items, but the first 40 items are multiple choice items. And then the remaining three items are free response items or constructed response items. So as you may guess, those multiple choice items are scored either 0 or 1. Correct or incorrect. And those constructed response items or free response items are scored from 0 to 9. So there are actually 10 categories for those three items. The number of examinees were 5,000. And then in this particular activity, we will consider the cause of multidimensionality as a item format. So we kind of assume that those 40 multiple choice items will measure something different from the other three constructed response items. Okay. Okay, so for the multiple choice items, we're going to use a 3PL model, three parameter logistic model. And then for those three free response items, we're going to use the graded response model. Okay. All right. So let's review the activity process. Like we can go back to the slide where we discussed the overall procedure of implementing the multidimensional IRT observed score equating. So we'll first calibrate items, meaning that we're going to estimate item parameters, and then we'll construct the conditional distribution using those item parameter estimates. And then our final goal is to find the marginal distribution by integrating or summing all these conditional distribution over the latent trait ability distribution, right? And then once you find these two marginal distributions for form X and form Y, we'll do the equipercentile equating to find the final equating relationship. So in this activity, we're going to use the flex mode to estimate item parameters. That's the first step. And then also there is a function that in FlexMerge that allows us to find the marginal distribution from using that estimated item parameters. So we'll again use the FlexMerge to do that work. So once we get those marginal distributions from the FlexMerge, we'll use that as input for the next step, which is going to be conducted using raise RG equate. So under to do the equipercentile equating, we're going to use raise RG equate. Okay, so there are three steps for this process. So if you open up this Google Drive, you will notice that there are actually three folders, but I hope you can combine the FlexMerge folder with the data file folder so that you have both FlexMerge commands as well as the data here in the same folder. Okay, I'm gonna run the first syntax, which is going to be this one, ssx.flexmerge. What is this one? Try this again. What's happening here? Oh my gosh, I don't know what it is. Okay, I'd like to see the syntax, but anyway, if you open this up, you will see this syntax. So let me just go over the syntax first. Okay, the first part is going to be under project, and then you can just type in whatever title you would like to have for this project. And then this is where you specify the quadrature points and the range. So if you have 41 and comma 6, that means you're going to use 41 quadrature points, and then the range for that quadrature point is going to be -6 to +6. And then here is going to be the important piece you may want to look, kind of change. So this is where this is the data file name. So if you use different data file, you need to change the name of the data file. And then this is where you name each variable. So I'm going to have MC1 for the first multiple choice item. And then I'm going to have FR1 for the first free response item. Okay. And then there are 5,000 examinees in the data set. And here you define the number of dimensions in your model. So because I have a latent trait associated with the multiple choice items and a factor or latent trait associated with the free response item, there are 2 dimensions here. And then you also need to give the number of categories for each item. So from for all these multiple choice items, there will be 2 categories, score categories. And for the free response item, there will be 10 score categories from 0 to 9. And then here is where you specify the model, the IRT model for each type of each item. So for multiple choice items, as I said, I'm going to use the 3PL model. And then for the free response model items, I'm going to use the graded response model. And this is where you need to provide the number of categories again. Okay. All right. This is where you will provide the model specification. So here you can see it starts from fix these, right? Fix MC12, MC4, MC4T, FR1 to FR3 slope. So if you have that line, the command, that means that you're going to fix all slope values to 0 so that you can fully estimate the individual items to load only on a specified vector. Okay, so because we have multiple unidimensional parts, we want to estimate the specific parameter for a particular factor associated with each item, right? So we want to first fix all slope values to 0, and then we'd like to free individual items to load only on the appropriate vector. Okay, so you need to have this first, and then these 40 items will be freely estimated to load on the first vector. These 3 items will be freely estimated. I mean, the slope for these 3 items will be fully estimated to load on the second factor. And there is a covariance factor. So if you have 2 latent traits, you can have the variance covariance matrix between factors, right? So COV 2.1 indicates the correlation, or probably the covariance between the factor. Okay, it's going to be a covariance between the factor, right? Because we're going to use a 0, 1 for both factors. Basically, it's the same as the correlation. But if you have multiple, more than 2 dimensions, like say there are 3 dimensions, you need to have free COV 2.1, free COV 3.1, free COV 3.2, because there are 3 pairs, pairs of correlations or covariances among those 3 factors, right? Because we only have 2 dimensions in this activity, we'll have just a single line of this free command. And then next, we'll have specify some prior distribution for item parameters. So there is like usually we often have trouble with estimating parameters for the guessing parameters. So I often specify the prior for the guessing parameter. And then there is a prior for slopes for both MC and FR. Okay, so if you run this, hopefully it's working. Okay, oh, here it is. So if you run this, so let's see, this is what we have, right? If you run this, it will take a while to estimate parameters because it's 2-dimensional. It's not like a unidimensional, so it just takes a while to get the estimates, but not much because it's 2-dimensional. But if you have like 3-dimension, it will take much longer time to estimate item parameters. Okay, so that's what so here we have 2 more new files, right? Generated from running this analysis. Let's look at the IRT. Can you see this screen? Okay, thank you. So if you open that IRT .txt file, you will see that the models that I specified for each item, parameter, the prior for each item, and then there is an estimated set of estimated item parameters, and you will see there is the latent variable variance covariance matrix. So basically, that's the correlation. I mean, as I said, it's it's basically a covariance, but because we specify each factor to be on a 0-1 scale, this is actually the covariance and correlation. So it should be the same, right? The correlation between the factors like MC trait and then FR trait is 0.47, which is very low, right? The correlation between these two factors is about like 0.5, which is very low. You see some fit statistics here. And what we need is, so we just finished the first part. We just estimate item parameters, right? The second part is we want to get the marginal distribution using those estimated parameters. As I mentioned, we can do this using FlexMert. So if you open the other FlexMert file, SSSCO, SS underline SCO, then that's the syntax that will give us that marginal distribution. Ooh. Okay, right. So what we're gonna do is we're gonna do the scoring using that parameters. So you need to first estimate item parameters, and using that item parameters, using that information, we are going to estimate the marginal distribution. What we need to specify here is the data file name, the original data file, and then the variable names. I don't think it's necessary, but I often just do it just for safety. And then the number of examinees, the number of dimensions. I think the required keys to run this syntax is this one, and then these parts. Okay. Right. Let's run this syntax. It's a bit quick. So you will get this result. If you look at the output file, you will see there is a table showing the sum score to scale score conversion. What we need from this table is the probability here. So here is the summed score, and here is the probability. As you can see, here is the EAP estimates, but we don't need this value. We just need the marginal distribution. So we don't it doesn't matter if you're going to use ML or like EAP or whatever, but because like our goal is not to estimate or score individuals, rather we're going to, our focus is to find the marginal distribution. But I believe only that syntax, oops, sorry. Only this SSC comment will give this conversion table. So that's why I use that one. Basically, we'll take this out as a marginal distribution. Okay. So if you go back to the slides, I'm going to use this marginal distribution as an input for the RAGE-RG equate. So the next step, as you recall, is going to do the equal percentile equating using that marginal distributions. So we're going to use this probability, the marginal distribution, as an input to run our RAGE-RG equate. So I just ran analysis using form X dataset, but you can do the same procedure for form Y, which is the old form. Okay, so I basically copy these values into this input file for RAGE-RG equate. Yes, right. So FlexMert used the Lurg and Wingersky formula to get this marginal distribution. Right, so here, if you look at the RAGE-RG equate, so now we've switched to RAGE-RG equate folder. If you go there, there is TXT file named RAGE-RG equate data. And the first column shows the sum the score 0 to, I guess, like, I don't know, 67 for this case, for this example. And then the second row represents the marginal distribution for the new form. And then the third column represents the marginal distribution for the old form. So again, you can do the analysis like item parameter estimate and you can estimation, and then get this, marginal distribution using the Flexmer syntax that I shared. I also so I got these results from that and then the last column shows the scale score. Okay. In practice, I think most people are interested in, I mean, the focus is on a scale score, not on raw score, right? But in this example, I just used raw score as like a, as a demonstration purposes. But like in practice, we often focus on a scale score, right? So that should be the major interest. This part should be the major interest. But anyway, if you open the file called win.ctl, let's go to this folder and open this up. This is the control file to run the RageRG-Equate. Okay, so basically RageRG-Equate, what it does is to do the equal percentile equating, like all different kinds of, I mean, when I say all different kinds, it also allows you to do the pre-smoothing and post-smoothing. And also there is a function for linear equating as well. So basically what we're going to do is to use this program to get the equal percentile equating result. Okay, so let's look at the syntax. As I said, columns to be read is going to be the second, third, and fourth column to indicate the new form distribution, the old form distribution, and then raw to scale score conversion. And then the scale score goes from 1 to 36 with the increment of 1. Okay, and then here is where you specify the input file name. We have RageRG-Equate underline data.txt, that's the input file name. And here is where you specify the output file name. Okay, whatever name you'd like to have. I have RG-Equate out. Okay, for this part, it doesn't really matter what you specify, because we are not interested in getting results for pre-smoothing, post-smoothing. Okay, so I'm gonna just focus on these parts. Okay, let's run the analysis. So because I have already prepared the input file, I can just run the program. So here you need to type in the control file name, not the RG-Equate the input file. Okay, so it's win.ctl, then run it, and you will get this output file. Okay, as I mentioned, we are not interested in getting results for pre-smoothing or post-smoothing, so these parts will be somehow irrelevant to our analysis, and we're going to focus on this column. That's the column that shows us the final equating relationship. Okay. So when I go back to this slide, please let me know if you have any questions about this activity. Okay, I'm sure it's a bit straightforward because I have already provided the syntax files for all these analysis. So you can simply run this analysis on your end. Right, so this is the final result, the no smoothing section, the column. Some practical considerations. So in using multidimensional IRT equating procedures in practice, I'm sure, as far as I know, there is no single testing company that uses multidimensional IRT equating as part of their operational work. But if people see a value of using this advanced technique, these are the kind of like considerations that you may you may have, and I just listed these kind of elements based on my research experience. First, of course, we need to do the dimensionality assessment, because the use of multidimensionality, multidimensional IRT models heavily relies on the degree of multidimensionality of the data that you have, right? So people often do the script plot, inspection, like visual inspection of this script plot. You may also do the parallel analysis to identify the number of factors, the significant factors in the data, or you can look at the latent trait correlations. So as I, presented or like discussed earlier with the output file from the FlexMert, you can look at the variable between variable correlation and see if that is low enough to consider the multidimensional approach. You can also look at the disattenuated correlations. The previous research kind of collectively indicates that the benchmark of having different results or having better results for multidimensional approach is the correlation of 0.8. So if this correlation is lower than 0.8, we may kind of anticipate that the results from multidimensional IRT equating will provide better results than the results from the unidimensional approach. So that's the kind of like, so far in the literature, the studies have demonstrated. So if you're working on a testing company, and if you see a low correlation among factors, meaning less than 0.8, then you may consider the use of multidimensional IRT equating. One thing that I had struggled with in doing my dissertation was the estimation process. So with our example today, there were only like 2 dimensions. So it just takes, it took about like, I guess like 30 seconds or 20 seconds to get the, estimated parameters. But in my dissertation, I used 3 dimensions. And then there was a common item non-equivalent groups design. So I used concurrent calibration, meaning that I calibrate both new form and old form simultaneously using the concurrent calibration. So it took about 6 to 8 hours to calibrate a single data set. And it was because it was a simulation study. I had to replicate that procedure like over like 1,000 times. And obviously it took like a while for me to complete that estimation process. So that's going to be the issue with using multidimensional IRT equating. Like I think if you have more dimensions in your data structure, it's going to be harder to get the item parameter estimates in a limited time. So there is Metropolis Hastings Robbins Monroe method developed by Li Chai in 2010. So I used that method, which you can specify using a FlexMert. It's known to be a better estimation procedure for higher level, higher dimensional data structure, but still it took a while for me to get final estimated results. Also, as I already discussed, some models has this confirmatory nature. So for instance, like the simple structure IRT model, you need to have the a priori data structure design, right? Prior to analyzing the data. So this model has to be determined by the table of specifications. It's not just like, okay, I look at the data and like empirically, okay, these items seem to, get together, and these item, form another cluster. So I'm going to use this infrastructure to, to analyze this data set. I don't think that's going to be justifiable in practice. So I believe the model has to be determined by the table or supported by the table of specifications, like the item format or the item contents or like test lists and so forth. Right. So there was a question from one of the attendees about the common item, about the linking procedure for this multidimensional IRT equating. So here, let's see. We know that under the unidimensional, unidimensional approach, we need to find the slope and intercept to find, under the common item non-equivalent groups design. When we do the linking, IRT linking, we kind of find the slope and intercept to put the item item parameters on the same scale between two forms, right? So that's going to determine, well, we need to determine the origin and the unit of measurement to do that, right? So the similar components exist for linking, for multi-linking, multidimensional IRT linking, which are named as like translation and dilation. But there are two additional components that we need to kind of equate or link, which are correlation and rotation of the axis, the coordinate axis. Often the correlation issue can be resolved by setting those correlation to be 0 among factors, but the orientation of the coordinate axis, like that's the element that adds some complexities of doing separate the multi-linking. So basically, there is a literature and studies that suggest or propose the multi-linking procedure with the separate calibration, which is presented here, like Oshima, Davey, and Lee in 2000. But because that causes some complexity, I try to avoid that complexity in my dissertation, and that's why I used concurrent calibration. And I believe that's why most common item non-equivalent groups design using multidimensional IRT equating in the literature used concurrent calibration to avoid that separate calibration complexity. The complexity associated with that separate calibration. So I thought that this is where we can do more on, in terms of the research, or broadening our, understanding how, the merge linking with the separate calibration can work with this, multidimensional IRT equating. So in this slide, I'm gonna kind of like, provide you the potential research areas based on my research experience, and that's one thing that you might want to kind of take a look. And the second one is, again, the number of dimensions. That's the issue with my, was not an issue, but was more like a barrier or obstacle in doing the research in a short amount of time. So if you look at the literature, you may notice that most of the research was done using like 2 or 3 dimensions. Like I don't have a chance to look. I didn't really see studies that use like more than like 4 dimensions, to my knowledge. So if you want to, apply this equating methods to real practice, there might be some cases where we need to think about, like 4 dimensions or 5 dimensions or even higher, right? But because current research, current literature has not explored that higher level of, higher number of dimensions so far, that's where we can do more on that. And quadrature points and weight, that's gonna be the problematic point, because if you increase number of dimensions, the number of possible combinations over those like quadrature points, like it's dramatically increases, right? So like I kind of, you know, presented the form of the quadrature point for two-dimension cases, right? Like 41 quadrature points times 41 quadrature points, it's gonna be 1681. So if there are 41 quadrature points for one dimension, and if you have two dimensions in your data, then it's gonna be 1681 quadrature points. But if you have three dimensions, that becomes 68,921 quadrature points, which is, you know, dramatically higher than, you know, two-dimension case, right? So so parameter estimation procedure should be kind of enhanced to for us to better you know, work on this research area. And I also, as I reviewed the you know, literature, I also noticed that differential multidimensionality has not been examined in the literature. Meaning, so when I say differential multidimensionality, what if say there are three dimensions, and then a correlation between the first dimension was like first two dimensions was 0.9, but the third dimension, I mean, the correlation between first and third was like 0.6, and then the second and third was like 0.7. So that's going to be the differential multidimensionality, right? So those first two dimensions is going to be more like unidimensional, but then the third dimension is going to cause, you know, lots of like multidimensionality in the data, right? That's going to be the first differential multidimensionality. None of the, I believe, the previous studies have explored the impact of that differential multidimensionality among, you know, using the multidimensional IRT equating methods. And then obviously there is one more component, the between group differential multidimensionality. So what if the a group, like an old form group, has like almost like unidimensional data, and then the other, like a new form group, has like very multidimensional data? Are we still going to use multidimensional IRT equating for that case? This question has not been addressed to my knowledge in the literature. So this also could be a possible research area if you're interested in this field. So there is one question from Jake. To apply this equating method, does one need to check the factor structure to confirm the assumption of yes, right? So you know, I kind of listed the several methods. Like, you know, you can look at the discontinuous correlation, latent trait correlations, or if you can do like CFA to see if the data, you know, fits the model you specified. Great question, thank you. The very last piece of my presentation today. So again, for the full MERT models, we still don't know how to resolve this issue, how to approximate the relationship between a set of theta on two forms. So nobody has explained or provided answer to this question yet. So I hope that somebody can do it in the field such that we can broaden our understanding in the field. One thing that I like to highlight is I know it's going to be difficult to use multidimensional IRT equating in practice, I mean, in operational setting. So many people ask, why do you do it? As you know, it's gonna be not used in practice. What I believe is that if you have better understanding of this procedure and know which condition it provides better results, I'm sure we can use this as like a backup, equating method. And then, like, whenever you do equating, you can implement the unidimensional IRT equating procedure as usual, and then also do the multidimensional IRT equating to see if how results are different from each other, right? So that's my like hope. And to do so, we need to do more research to kind of know, what are the conditions we need to kind of consider to use your multidimensional IRT equating. And as I don't know if you may know about it, but if you look at the multidimensional IRT literature, people say that the multidimensionality is not a property of a form alone. It's the property or characteristics of both a group and a form. So if I say the test was multidimensional, it doesn't mean that the form is multidimensional. It's going to be somehow combination of the group characteristics and the form characteristics. So even if you use the same form, for some group, the data could be multidimensional, like more multidimensional. And for some group, for the other group, the data could be rather essentially unidimensional. So it's going to be the combination of those two components. And that was kind of like a theoretical and conceptual question that I had while I was writing my dissertation. Like, can I view this multidimensionality as a characteristic of a form, or a characteristics of a group? But I think the answer is still inconclusive, but we know that it's going to be the combination of those two. And to use the equating method, multidimensional IRT equating methods in practice, we will need to kind of ensure that that was primarily caused by the form characteristic, not by the group characteristic. Because if group, if the group changes, then the use of multidimensional IRT equating may not be applicable for some groups. So that's the practical considerations that I had, and possibly researchers can address this question as well. And I know, some testing programs, are more focusing on kind of classifying examinees into, fail or pass, or, multiple categories. So the impact of implementing the multidimensional, IRT equating on those classification indices has not been explored yet. So probably that's one possible research area. And we also need to, think about the impacts on reported score, which is going to be the final output from testing. So that's what I have for today. And this brings to the end of this session. Yeah. In that case, equating could not be possible since forms are not measuring the same thing. Not sure. Still, they can measure the same thing, right? But the structure, I guess the point here is, like, the focus is the data structure, like the relationship between those factors. That could be the question that we need to ask. Still, they can measure the same thing, but the relationship between these factors can differ, right? So after this, I have a set of literature, and that's it for today. We have about 10 minutes for Q&A. So if you have any questions, please unmute yourself or type in to the chat box. I guess I addressed most of your questions during the session. So again, I really hope that I can have more colleagues in this field. I just had a publication from my dissertation and a couple of other manuscripts under review or in preparation, but because there are not much known pieces in this field, I'd like to share my understanding in this field. And draw your attention to this field to broaden our, understanding this field. Okay. Can you tell us something? Can you tell us something about the values of the SE on the second column at the very beginning of the output file under the title of route score conversion for post smoothing? Okay. Oh, these are, yes. I guess it's because there are many observed data points at the bottom. Yeah, I don't know why it's so large. I'm sure it's a standard error for equating. Well, yeah, it's a bit large. Thanks for pointing out this. I didn't really notice it, but it looks very large. In separate calibration, do you have any ideas dealing with correlations between two factors? Yes. So if you use this method, there are some procedures developed by researchers in early 2000 like 20s. They their procedure kind of incorporate that correlation or the rotation of the axis into consideration. Yes. Okay, if there is no more, okay, is Flexmer able to handle margin distribution of? Yes. So in this case, in the activity that I had during the session, we only consider the simple structure multidimensional IRT model, but I can provide you the syntax file for bifactor model if you'd like, and I also have the syntax file for MERT as well. I mean, I'm sure it's going to be straightforward to set up the syntax file for unidimensional model, but I can provide you more syntax files for each of the models that I explained today. So yeah, but if you can use that, syntax file and run a similar procedure, the analysis through the similar procedure, then you can, get the marginal distribution for other models. So just let me know if you want that syntax file. I'm gonna share it with you. Email me. I'm sure you have my email address. So any other questions? I guess it's the end of the session. And personally, I really enjoy leading this session as an organizer. So I appreciate, I thank myself to teach, to invite to teach this course, this session as an organizer. And I hope you also enjoyed this session and see some potential areas for research and see some potential, application pieces of multidimensional IRT equating in practice. So if you have any questions about my dissertation, about my research, about the contents covered during the session, please feel free to reach out to me via my email. And then the slides will be made available right after this session onto the Google Shared Drive. And thanks for joining us today, joining this session today during your busy day, and hope you have wonderful Thanksgiving break. Okay, and we'll see you at the last session, which is going to be led by Ye Tong in 2 weeks. Okay. Right. Thank you all. Bye.